Hi everybody, Dr. Blum here. I'd like to start to talk about VSEPR, or valence shell electron pair repulsion theory. And it's VSEPR, or VSEPR for short. And this is part 1. And we're going to talk about VSEPR as a theory we use to take Lewis structures and convert them to 3D models. So today we're going to talk about the importance of molecular shape. So we're going to take a Lewis structure like the one for water, H2O, and convert it to what this looks like in 3D space, and why that is important. Okay, so 3D shape is important for both physical and chemical properties of a molecule. And when we talk about physical properties, we can be talking about things like density. Remember, density equals mass over volume. We can talk about phase change, boiling point, melting point, things like that. So boiling point, melting point, etc. We can also talk about solubility. So we have introduced the idea that like dissolves like in past chapters. And so we can talk about whether something is hydrophobic or hydrophilic, meaning will it dissolve in water, will it not dissolve in water? And those are the type of things that we can determine from the 3D shape. In terms of chemical properties, we can look at reactivity. So how likely a molecule is going to be able to react, the type of reactions that it undergoes. Also, things like working with catalysts. Catalysts, especially enzymes, tend to be very heavily focused on the shape. So today I'd like to talk about 2 examples about when shape is important, but you can extend this to multiple different problems. And the first example I'm going to talk about, is the shape of water. And you may remember that there was an Oscar-winning movie entitled The Shape of Water that had nothing to do with the shape of water. I don't know what it was about, but it was certainly not about the shape of water. Because the shape of water, and this doesn't give any spoilers away if you haven't seen the movie, but the shape of water is bent. And so water is a Lewis structure with oxygen bonded to 2 hydrogen atoms, and there are 2 lone pairs on the oxygen, and this causes oxygen to be bent, and it has an angle of around 105 degrees. Other things we know about water and the properties of water. So I said it has to do with reactivity. We're going to focus here on physical properties. Water has a molecular weight of 18 grams per mole. Boiling point is 100 degrees Celsius. The melting point of water is 0 degrees Celsius. We also know water is what we call a polar molecule, and I'll talk about why that is in a second. Another molecule I want to compare this to is carbon dioxide. Carbon dioxide has a geometry, has a Lewis structure with carbon in the middle and oxygen double bonded. Again, oxygen still has the 2 lone pairs. And carbon dioxide happens to form a linear geometry. So I'm going to write H2O. It's bent over here. And so because it's linear, it has 180 degrees. And so some properties about carbon dioxide. Carbon dioxide has a molecular weight of 44 grams per mole. Carbon dioxide at atmospheric pressure does something called sublimation. So sublimation is where it goes directly from solid to gas. And that happens for carbon dioxide. If you've ever gotten dry ice, that's solid carbon dioxide. Carbon dioxide undergoes sublimation. This transition so the sublimation point, or SP, is at negative 78.5 degrees C at 1 atmosphere. The other thing about carbon dioxide is nonpolar. So pretty distinctive differences between these 2 molecules. And a lot of this has to do with the different shapes. So the fact that water is bent gives water this property of polarity. And so what is polarity? Polarity is separation of charge. If we remember that oxygen sits way over on the right side of the periodic table, which actually makes oxygen very electronegative. Electronegativity means it really likes electrons. And so it really likes to suck those electrons over. And because of that, it becomes partially negative. So that little d means partial. So it's not like an ionic compound where it completely rips away the electron, but it is partially negative. And because oxygen is taking all that electrons away from hydrogen, hydrogen is left as partially positive. And so both hydrogens here are partially positive. This difference in charge, this separation of charge, causes this polar effect, and there's a net dipole, kind of like a magnet, that's going up from the hydrogen toward the oxygen. This means water almost behaves like a magnet to itself. Other water molecules are indeed attracted to it. So if I have another water molecule, here, and it's also partially positive over here. Partially negative. And so if we remember, opposites attract, positive, negative attract. So there's an attraction here. And this attraction between water molecules is what gives water a lot of its features. Because water is attracted to other water molecules, that means it takes more energy to separate water molecules from each other, which gives it, for its molecular weight, albeit very small, it's a very light molecule, it has a fairly high boiling and melting point. So we would not have this difference, though, if we go back and we look at carbon dioxide. Carbon dioxide also has oxygen on it. So, and carbon becomes partially positive, and that oxygen, again, is partially negative over here, and that oxygen is partially negative. But because carbon dioxide is linear, this oxygen is pulling this way, and this oxygen is pulling it that way. These poles, these separation of charge, actually cancel each other out. And so what happens with this molecule is actually non-polar, because this is pulling that way, this pulling that way. If you imagine two ropes pulling exactly opposite from each other, you would see that that center, that carbon atom, doesn't move, as opposed to water, which is at an angle. And so in this case, we're actually pushing toward that oxygen, but because we're pushing at an angle and not directly opposite each other in the case of the linear, the oxygen will actually have a net movement up. So here there is no net dipole. And the molecule becomes nonpolar. And so you can see the fact that there's not as an attraction between carbon dioxide molecules and other carbon dioxide molecules, which means that the transition between solid to gas occurs at a much lower temperature. You don't need as much thermal energy to separate these molecules from each other into the gas phase. So at room temperature, we find carbon dioxide in the gas phase, while at room temperature, water is liquid, and that because of the shape of water. Now I want you to have a little thought process for a second and think, wow, what would happen if water were linear? Life as we know it would no longer exist, because water would definitely be a gas at room temperature if water was a linear molecule and was not polar. So the importance of shape and understanding molecular geometry is very critical to understand this type of property. I want to give one more example, and this example is based on an enzyme example and a drug molecule, atorvastatin. So atorvastatin is Lipitor. At one point, it was the world's #1 selling drug. It's made by Pfizer. The statins are now generic. But a little bit about how the statins work. The Lipitors, if you have high cholesterol, you will take Lipitor to lower your cholesterol levels. And Lipitor works by blocking part of the pathway to make cholesterol. So if we take a look at this pathway to make cholesterol, acetyl-CoA is a metabolic intermediate. And it is a precursor molecule to this molecule HMG-CoA, which is then reacted into mavonic acid. Which undergoes several more reactions, ultimately making cholesterol. And we have enzymes in our body that facilitate a lot of these steps. And we're going to look specifically at this reaction, HMG-CoA to mavonic acid. And this is an enzyme known as HMG coenzyme reductase. An enzyme is a biological catalyst that is used to facilitate this reaction. So basically, it's a helper molecule that will help this reaction from HMG-CoA go to mavonic acid. And so normally what happens, and we like to represent enzymes. So I'm just going to represent this enzyme as a little Pac-Man-like molecule. Hey, Pac-Man. This is my enzyme. And enzymes are very shape dependent. So one thing about enzyme is that they're very specific to the shape of the molecule that they are helping react. So let's say HMG-CoA, make him pink. Looks like a nice little pizza pie here. And normally what happens, so this is my HMG-CoA. And normally what happens is this will go, and the enzyme will bind. A little Pac-Man thing. He'll bind. Here it fits really nicely in. And then we end up back with enzyme. So the enzyme gets to be reused for the next molecule to come along. Plus, now we're going to have our product, which I'll give it a different color. We'll make it blue. So now our product, and we'll make that look a little bit different. And so that's my product. And then this goes on to make cholesterol. But with Lipitor hanging around, what happens is we have a Lipitor molecule. And so Lipitor, let's say Lipitor looks like this. And with Lipitor coming around, it's now going to compete for this same part of the enzyme. And Lipitor can come in. And I have this big old orange molecule here. And this will block access to my HMG-CoA. And with Lipitor, I will stop this reaction and it will no longer produce cholesterol. So as long as you have Lipitor in your system, we have what's called a competitive inhibitor, and the Lipitor molecule is fighting for spots in that enzyme and blocking access to the natural reactant HMG-CoA. And it can only do that because the shapes are similar. So I'm going to show you a picture. So in this image, I took an image from the University of Texas, and I encourage you to go to this website that's linked in this video to look at this site. It talks a lot about the Lipitor mechanism. This is actually the yellow part here. This is the enzyme here. And in the middle, this is Lipitor. And you can see that this is also, this is Lipitor here. And you can see the parts of this molecule. So this is the part that's kind of sticking out of the enzyme. And this is what's doing the blocking. And this is what's in the binding region. This is the native substrate, the HMG CoA. And a lot of times we talk about enzymes, we talk about them as a lock and a key. And you can see in this molecule, there is kind of similar parts here, that double bond oxygen. And this is what we're mimicking with Lipitor. It's just this tail end of the molecule. And what this is doing, this Lipitor molecule is getting in there, and all these big bulky rings and these big bulky groups are able to block the native HMG CoA from binding. And that is really the mechanism on the importance of shape for something like Lipitor. All right, please join me in the rest of the videos where we show you how we actually take those Lewis structures to complete 3D models from them. And I hope you have a better understanding now of why we think this is something that is very important in understanding your molecular structure. Thank you.